everybody. Oh, geez. Okay. Hello. Good morning, everybody. My name is Minnie, and we are the smoke team. So today we'll be presenting improving wildfire smoke predictions in BC using convolutional neural networks. And this slide just shows everybody who's involved in the project, and we want to thank everybody on this page. So we'll just introduce a little bit of the background. Wildfire, why is predicting wildfire smoke important? So essentially, wildfire smoke leads to pollution that can contribute to a variety of health conditions, such as the ones you can see on the screen, as well as premature mortality. And so this issue also is challenging. So this prediction is challenging because there are many uncertainties in finding out the exact fire location, how it grows, and the biomass around this fire, and also the plume height. So there's a number of reasons why predicting wildfire smoke is challenging. To give a bit more background in Canada, so we currently have 2 wildfires forecasting systems that use statistical modeling to predict wildfires. So there's one that you can see on the right there. That's the blue sky prediction. From a machine learning perspective, the ground truth measurements are sparse within BC, so that makes it challenging to train the model. Oops, sorry. So our goal, overarching goal, is to improve wildfire smoke prediction using convolutional neural networks to see if it's a feasible way to predict smoke. And to achieve this, we have accomplished 3 objectives. The first being developing an automated download suite that can download directly from different sources. And second being a developed data pipeline that can support and process these input variables. And lastly, we present the result of our feasibility study on whether CNN, convolutional neural networks, is a viable method to try to accomplish this task. So the data sets that we used, so there are so many different types of data that you can use to try to predict wildfire smoke. And initially we were presented with 6 different data sets, and we were very ambitious and wanted to do them all. But then we realized, so you can see we wanted to predict based on existing smoke forecasts and some satellite imaging. However, we realized that that was a little bit too ambitious, so we stuck with 4 due to time constraints, really. So we're predicting based on these 4 data sets. So the first one being firework, which is an existing smoke forecast, and that gives you the hourly predictions of PM 2.5 based on fire location and the fuel consumption. And blue sky is similar, except that it adds meteorological data to that. And the smoke plume imaging is based on satellite. And so you could see that the analysts draw these. So those skills of drawing in kindergarten actually is useful sometimes. And then lastly, fire radiative power is based on satellite imaging of fire intensity. So these are the 4 data sets that we essentially chose to use for our CNN. And I will pass it on to Ashu to talk about the download suite.
Oh, sorry, I'm just navigating through this thing. So can everybody see the slides here?
Yes.
Perfect. So since the midterm presentation, the package is more or less being completely refactored to make it more modular and to incorporate new functionality like custom data ranges and checksum verification. So this is what the package structure looks like. And in the UTIS package, we have all of the code that handles the server side, the downloads, local file management, error handling, and so on. So all we have to do in the main program is to fetch your URLs and download the files in the particular way that each server likes to have it done. So although this diagram looks complicated, in truth, it's actually structured much more like this, where the downloaders are built upon the classes that fetch your URLs, and the main simply calls the run method on the downloaders. So what does this all mean for the user? Well, it means fewer download issues and due to automated error handling. There is an immense boost in speed by utilizing multiple threads and smart downloading techniques. And on top of that, it runs on an efficiently managed thread pool, and this makes it suitable for running on head nodes of batch processing systems as well as VMs and PCs. In fact, with a single command, after which we all went to sleep, we downloaded over 240 gigabytes of data and around 28,000 files overnight. And that was just 2 years worth of data. So apart from that, here's a glance at what the command line utility looks like. It's just a single command to which you feed a config file. And with that, I'm going to hand it off to Brandon to talk about the data pipeline. Brandon?
Can everybody see my screen? And my little pointer?
Yep.
All right, cool. So here we are at the data pipeline. So basically the data pipeline's primary purpose is to go from the raw data files we get from the download suite and turn them into tensors which our model can train off of. So we basically do this through 3 core steps that you see here. First, we have a parsing step, which is basically moving things from the raw data files into Python's memory. Second, we have a cleaning step, which is turning those things in memory into some saved out space-time grids. And third, we have an amalgamating step, which is basically taking slices from those saved out grids and stacking them into a tensor, which our model can train off of. So the pipeline also has a secondary purpose of basically implementing manual control over this 3-step process. So this sort of acts like valves to our pipeline and lets us control which data flows through the pipeline and how the data basically ends up at the end of it. So moving on to the code base, here we can see a UML diagram of our finalized pipeline structure. These dashed lines over here are dependencies, and these solid lines are extensions. And we can actually see where our 3-step process happens in the code base itself. So up here we have a parsing suite. Basically we have one parser for every single one of our datasets file formats. And these each contain the process necessary to turn a raw data file into a standard object in Python's memory that we see here. Second, we have a cleaning suite. We have a dataset specific cleaner for each of our data sets. And these basically rely on an individual parser and processes stored in these generalized cleaners up here to turn our raw data files into these saved out 40 grids in this object right here. And finally, for our amalgamator over here, this carries out our amalgamating step. And it basically relies on the saved out grids and the NOAA processing branch to convert those things into our finalized PyTorch tensors, which our model can train off of. So this finalized code structure actually has a lot of advantages over our old pipeline structure that we showed in the midterm presentation 4 weeks ago, which we can see right here. So first of all, obviously it's complete. We have the NOAA processing branch done and the amalgamator done, which means that we can access NOAA data, and also we can make our finalized PyTorch tensors. But also there's a number of advantages in the more clean and organized structure of our finalized pipeline. So this can be seen in various points throughout the code, but mainly in these cleaners and in the tools over here. So in the old pipeline structure, we basically had the processing for the data files to turn them into grids stored in every single one of our cleaners. But in our new pipeline structure, we've basically abstracted that out. which reduces coupling in our code and basically makes everything cleaner because it's a lot easier to maintain one main object. And second, for the tools, in the old pipeline structure, we kind of had a mess of various tools, but in the new pipeline structure, we've basically consolidated them into one tool that crunches down on across time and one tool that crunches across space. So this just gives an overall cleaner architecture. So with that, we can talk a little bit about how we actually run the code base. And here we see we have two major scripts. And these two things are the places where we have most of our manual inputs, those valves I mentioned earlier. So first we have the run cleaner script, which we basically use to run the cleaners and output these 40 grids that we're saving out. And second, we have the run amalgamator script, which allows us to run the amalgamator and allows it to pick and choose from these 40 grids and our NOAA processing branch to output some PyTorch tensors. So basically the run cleaner script gives us control over our space-time grid settings. So with the run cleaner script, we get to tweak things like our grid cell size or our time resolution. And for our run amalgamator script, these give us control over the tensor creation process. So we can tweak things like which data sets actually go into the tensors and date ranges we run the tensors over and things like that. So splitting things up in this fashion basically gives us an advantage in time because the cleaning process takes a ton of time to do. But if we split it up like this, we can basically clean once and then amalgamate to create multiple sets of tensors, which basically just prevents us from having to run the cleaning for every single tensor creation that we do. So with all of that knowledge of the structure and how to use it, a good question to ask now is how do we know that the pipeline actually does any of this? And for this, we have our testing suite, which tests the major components of our pipeline. So this basically guards us from any coding mistakes or any obvious errors. And we basically have three kinds of testing that we can do for the pipeline. So first we have full unit testing. So this is your edge cases, your various points and ranges, and your error catching. And we can run these on the crunchers and on the common data objects, basically anything that's not tied to a specific raw data file. And because the crunchers operate on arbitrary gridded data and the common data sets are meant to store arbitrary gridded data. So we can basically just run standard unit testing on those. We also have runnability testing, which I'm not sure if there's actually a proper name for this, but I've just decided to call it runnability testing. And this is basically piping an example file through our test object to see if what we get, or one, if the object actually ends up going through, and two, if what we get on the other end is what we would expect manually loading the file. So we can do that on our parsers and on our amalgamator. So on the standard data object that this produces and the tensors that this produces to see if we end up getting the result we want. And finally, we have manual visual testing, which we run on the cleaners. And this basically lets us diagnose the whole pipeline as a whole because the cleaners use all of the parsers and all of the tools with it. So for this, what we basically do is we plot the product of the cleaners, the saved out grids, alongside the initial data that should go into it. And we visually see if things end up matching up. So we can see that in this video here. Initial data is on the left side and the saved out grids are on the right side. And we're basically trying to see if everything in this box ends up on this side, which it generally does. Yep, so we've done that on a large number of saved out grids and they've all checked out. So with that testing and with the two other types of testing over here, we can be reasonably certain that the PyTorch, that the pipeline is doing its job well and producing good tensors for our model. So I will pass it off to Ren to talk about the model now.
Perfect. Slides. Nice. Okay, so there's a lot of work that's been done since the midterm. We didn't really get a chance to go into detail about the model during the midterm. And I'm pretty excited to present this because we've had a lot of really interesting things come out of this work over the past week. And it'll be nice to have a discussion and hear some of the thoughts of the experts on what these results might mean. But yeah, so I motivated the model a little bit during the midterm presentation, but again, at a high level, a lot of issues with previous models that have done this wildfire smoke prediction is that they don't preserve the necessary spatial inductive biases that are kind of important to facilitate learning of any model. So what we really want to do is we want to design a model which can use some kind of high dimensional image. So Brandon talked about these 4-dimensional kind of tensors. So we can think of this as some kind of high dimensional image of the area around BC. And these contain features that are relevant to wildfire smoke prediction, in our humble opinion. And this model hopefully will be able to efficiently synthesize that information and then kind of project that understanding back to a same image and be able to do PM 2.5 prediction over that entire image. So what would such a model look like? So this is what is in the computer vision literature known classically as a U-net. And you can see that it is named such because of this U shape. Without going into too much detail about what each one of these individual modules or kind of the fundamental theory behind why such an architecture works, there are two things that are important to take away from here. So one is you have this kind of what's called a downsampling arm here on the left and upsampling on the right. So the idea behind this is, let's compress this big image that is getting input to the model down to some kind of intermediate compact representation and project that back to the original image. And again, this is something that has been shown to work in a number of cases. It's more heuristic than actually founded in theory, but it works very well. And the second thing to notice are these arrows over here that represent skip connections. So what's actually happening here is that the model does some processing and then it saves the representation here, and then it does more processing, blah, 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 goes through the rest of these arms. And when it gets here, it actually concatenates this kind of processed step with the previous process step. And this kind of preserves information and prevents the architecture from kind of forgetting what was kind of more important upstream details as it goes through iterative layers of these processing steps. Right, so this is all fine and dandy. You input an image and then you output basically something that's effectively an image as well. Okay, so what's the problem with this? Well, the biggest problem is that, as Minnie mentioned before, these measurements are very sparse. So there are only a select few environmental monitoring stations over BC that actually have very good and very consistent predictions. So the initial idea was to say, well, maybe we can bypass this problem. Maybe we can just generate a mask of a binary mask of zeros and ones, which define clearly where we have the EMS values within our image, within our image grid. And then we just multiply the output of the model with this mask. And that should tell the model basically, the values that you're predicting in these locations are real, and the values that you're predicting in these other locations are not important. This is a naive approach, to say the least. It doesn't work primarily because of the weight sharing scheme within convolutional neural networks. If everything was what's called a fully connected network, then this would be fine. Zeroing out the predictions effectively zeroes out the weights that are associated with those predictions. But this is no longer true for CNN. So a more feasible idea was only to do predictions for 10 EMS stations throughout BC, which have the most and the most consistent measurements over the past 2 years. So this dramatically kind of narrows the scope of the project. And I think this is a theme that was prevalent in a lot of our work. we had 6 data sets. We ended up with going with 4. You know, we had this lofty idea for a fancy model that would do a lot of things. But in the end, we kind of brought it down to something that was more feasible to get results. Right, so this actually alone still doesn't work. You know, we did something ambitious even after kind of narrowing the scope, which was we trained on all of our data at the time. So the NOAA data, the 4th data set, wasn't available. But so we had firework predictions, blue sky predictions, and the MODIS fire radiative power kind of values over a grid defined over BC. And the cell size in this grid was 5 kilometers by 5 kilometers. And the total area of the grid, I believe, was something like 1,250 kilometers by 1,250 kilometers. BC is a big province. So yeah, as you can see from this learning rate curve, which is, you know, a good way of assessing how the model has trained. You know, on the x-axis, you have the number of iterations that we've gone over the data set. And on the y-axis, you have the mean squared error, which is a common loss function that you use for regression tasks like predicting PM2.5 values. So, you know, you see that the training error kind of plateaus around, you know, 200 mean squared error loss, which, considering the magnitude of these predictions, these PM2.5 predictions are, you know, on the order of 10 to the 1. You would actually do better if you just predicted zeros for everything. So it's not clear that this is working at all. And it's also very noisy. Okay, so clearly there's something wrong here. So the first thing we did was try to assess if this was a model-sided issue. Because it was a complicated model and we weren't sure if there were bugs there. So this data, this model was trained on another data set, which was a image classification kind of data set. So you have a bunch of scenes of mountains, forests, you know, cities, whatever. And you feed that image to the model, and then you try to predict the category that image came from. So on the left axis, you have cross-entropy loss, which is commonly used for categorical classification tasks. And on the right, you just have accuracy. So you know, lower on the left is good, higher on the right is good. And then again, on the x-axis, you have the number of iterations that we went over the data set. So you can see that kind of the, okay, I realize there's an issue with this plot, but essentially this curve that's going down is the cross-entropy loss. It's heading towards 0, and then the accuracy is heading towards 100%. So this actually did better than any other model that was on Kaggle where we obtained this data set. But anyways, so this gave us confidence that the model is working well. Okay, so maybe it's a data-sided issue. Now, the way that we assessed this was through the manual kind of visualization tool that Brandon mentioned earlier. And it was actually Ashu who made this very astute observation. And this is why it's important to validate your data like this. So you can see that this was our discretization attempt with 5 kilometer by 5 kilometer cells. So you can see this is the grid, this is the grid, and it gets turned into this kind of image over here on the right. And you can see that there are a lot of holes in the data. You know, it looks, there are a lot of stripes and bars, and there are clearly places where the data is missing. So this basically told us that the resolution that we were defining our grid at was too fine. So we made it coarser. And after we made it coarser, it looked something like this. So you can see that the data is much more smooth now. You know, there's no kind of discontinuous boundaries in between different cells. It looks a lot nicer, a lot smoother. And this gives us better results. So you know, instead of ambitiously trying to train on all 3 data sets at once, we said, why don't we do this iteratively with this new 10 kilometer by 10 kilometer cell thing. So much smoother training curves. You see that the training and validation loss on this data set heads towards 0, and it looks really good. Okay, but we're really concerned about results, right? The learning rate curve tells us something about training, but doesn't really tell us in terms of actual predictions on the test set. So I'm going to show you a series of slides over the course of different months throughout 2018 and 2019. There are 4 in total, I believe, for this model. And the main takeaways are that, you know, whether it be early fire season predictions like you have on this slide or later in the season, we tend to get pretty good results for different stations. Crucially, these stations are by city. So, you know, Abbotsford, I believe, probably has like 2 stations. So that's why they have the same title, but they are 2 different stations. So yeah, so this is, you know, April. You can see that in cases where, you know, firework does dramatically poorly, where green is the ground truth, our model is also bad, to be fair, but it is closer. And, you know, there are cases where this difference is just very dramatic. And this is from June. So again, you know, firework can overpredict in a lot of cases, and we can also get closer. But then, you know, if you look at Richmond, because we are basing this model only off of the firework predictions, you know, it's heavily influenced by that, and it can be bad as well. This is August, so probably, you know, closer to June, August, closer to peak fire season. These measurements, the performance on these measurements is going to be more important. And then finally October. So these weren't cherry picked, to be fair. It's completely random how I selected these. So they are pretty indicative of how the model performs. Right, so I mentioned iteratively adding data sets. Now, in machine learning, we often like to just add data for the sake of having more data. The idea is more is better. Just train on all the data that you have, use the biggest model you have, and results will get better. This is an example where that kind of works, but not really. So Blue Sky is problematic in that it injects a significant amount of noise into the training. So you can see on the right-hand side, this is what happens. I've reproduced the curve from a couple of slides ago with firework only, and this is firework and Blue Sky. So it does appear to be a little noisier. But then we have this interesting phenomenon where kind of the loss spikes here a little bit, and then it goes back down. And this is what is in optimization theory known as the double descent curve. So this indicates that the model is appropriately sized, and it's able to kind of achieve a better optimum. So this model, at the end of the day, is better, or should be better in theory, than the firework only model. And then we have a similar set of plots. So again, the takeaways from this series of slides is that, you know, we get reasonable predictions for different stations throughout the course of the core fire season, you know, from April to October. But again, Blue Sky injects a lot of data. This is the second takeaway. So Blue Sky data injects a lot of noise, and it has a significant amount of sparsity, both spatially as well as temporally. So you can see that here you just have no Blue Sky information. Blue Sky should be in orange, but you just get nothing. And it's not really clear if this is helping or hindering the model. And here you do get Blue Sky, but I would say Blue Sky is significantly worse than firework in terms of its predictive value, and also how helpful it is for the model. And here we have August, and then finally October again. So these are different times than the previous data sets, and that's because when you kind of cross-correlate these different data sets, you end up with kind of different timestamps for where there is data agreements. Right, okay, so that's all fine and dandy. This is a summary slide that basically quantifies the results that I've showed on the previous few slides. Sorry, this was supposed to be in LaTeX, but I guess I forgot a $sign, so it's not. But essentially, these numbers are the test set average mean squared error. So they represent the mean squared error that you can expect for any given station for any of these models on the left. So maybe I should explain this a little more. So firework is what the actual firework prediction is. and its deviation from the ground truth that we actually get from these monitoring stations. Blue Sky is the same for the Blue Sky data. Trained on firework only, sorry. And then model B, sorry, I'll move my pointer for a bit. Model B is trained on firework as well as Blue Sky. And then remember I mentioned that there's this issue with corresponding different time labels. When you incorporate more data sets, you inevitably end up with fewer kind of time stamps where there is data agreement. So the first column is the firework data set. And then the second column is what happens when we add Blue Sky. So you can see that our model, to be expected, actually does better than either the firework or Blue Sky predictions. And I say expected because these models are actually predictions in and of themselves. So in theory, to do as well as these models, all our models have to do is learn the identity function. And with a CNN and a complex kind of deep neural network, you're going to get some gains in terms of function approximation from these baseline models. So it's expected to do slightly better than them. But these results are okay. They're not great. I certainly wouldn't use them yet, maybe. But they're indicative that the CNN is indeed feasible to do this smoke prediction task. So this is fairly crucial, addressing the bias in terms of our data sets as well as the model. So I've mentioned that we've trained on only 4 out of the 6 data sets, but in fact, in my opinion, I don't even think 6 is enough. You need meteorological data, and you need kind of domain experts to tell you what to do with that data, to transform it into something that is a function of that raw data. And again, that requires domain knowledge, but it is fairly important. The argument maybe is that, well, firework and Blue Sky, they do take into account meteorological data. But what they've done is they've processed that data. If you think about it from a statistical standpoint, if you average a bunch of 4 values and you get a number, you can't ever get back to those 4 values without additional information. So processed data loses information in a lot of cases. And the second part is that this parameter sharing approach in CNN, it gives us interesting results, but it's not clear that it's doing anything about the principle. It could very well be doing some crazy nonsensical things and just getting numbers that look good. And it's not clear that this model scales either. We've only done predictions for 10 of the stations out of 60, 70. Does it work for these other stations? We don't really know. And moreover, even if it does work for these other stations, what about those populations that are not situated around these stations, especially in the far north of BC? Are we going to be able to give them accurate predictions about PM 2.5 levels? So that's not clear either. So this moves us into kind of recommendations and improvements. So the first thing is that there are a lot of things to do on the model side. I have no shortage of ideas on what to do on the model side. So the first thing is you can do what's called multi-headed prediction. You have different heads that kind of predict different things. And if you pre-train these models on more complete data sets, you might be able to handle this sparsity problem that I mentioned earlier. So the model might learn to fill in those intermediate values in between EMS stations where you don't have raw PM 2.5 ground truth values. And the second thing is you can address the sparsity more directly by using a convolutional neural network that is designed basically to deal with holes in images like this. But then, it's not really clear how to improve the data, right? Because we don't have access to the actual firework model or the actual Blue Sky Canada model. And again, we saw that with Blue Sky, it was injecting a lot of noise, and it wasn't clear that it was helping the model, practically speaking. So, more is in theory better, but maybe that's not the way we want to go. Maybe better is not more in this case. So, we should get more data sets, but we should do this thing that we've done throughout, which is to ascertain their quality both visually and quantitatively. So does it make sense when we transform it into this data input format that the model wants? And again, the second thing is to incorporate raw meteorological data into this model. I think that is all that I have. Yes. Again, this was an absolute pleasure to work on this project. It was hugely interesting. I think my teammates feel the same as well. We're happy to take any questions or discuss anything that we've talked about today. Thank you.